A submarine is a ghost of the deep. It can vanish beneath the waves and remain hidden for months, operating in total silence as a phantom of the ocean. But even a ghost needs energy to survive. Unlike a car, a plane, or even a standard surface ship, a submarine cannot simply pull into a neighborhood gas station when the needle hits empty. In fact, the process of fueling these machines is one of the most complex engineering challenges on the planet. If the refueling process is handled incorrectly, the results can be catastrophic, risking devastating fires, radioactive contamination, or revealing a secret location to the entire world. Here is the surprising truth. Some submarines must refuel every few weeks, while others can go their entire 30-year service life without ever taking on a single drop of fuel. By the end of this video, you will see the staggering multi-year operation required to replace the fuel inside a nuclear submarine, a process so invasive that engineers are often forced to literally cut the vessel open. There are two completely different worlds of submarine refueling, and understanding the gap between them reveals the true power of these underwater titans. How are these machines powered? First, what kind of submarine are we talking about? The world's navies use diesel-electric and nuclear-powered submarines. Both types of boats symbolize different naval fighting and technical ideologies. Many nations' navies rely on diesel-electric submarines. Conventional marine diesel fuel powers them. However, nuclear submarines use enriched uranium fuel rods in a high-pressure reactor to create nearly infinite energy. Refueling these two is like conducting open-heart surgery on a mammoth versus a quick petrol station stop. Diesel submarines use pipes and pumps to refuel, but with stricter safety rules. No fuel hatch or reactor hose connection are on a nuclear submarine. A nuclear boat's refueling may happen once in a generation. A nuclear refueling can take years, while a diesel one may take hours. But before we examine inside a nuclear reactor, how does a submarine safely take on thousands of liters of explosive liquid fuel without becoming a floating fire hazard? When a diesel-electric submarine returns to a secure naval base, harbor, or submarine tender, it refuels. Precision is needed for this delicate operation. To maintain a stealthy profile, submarines have gasoline connection terminals on top of the hull or below watertight access panels. These filling ports receive heavy-duty gasoline lines after the submarine is docked. This is much harder than truck filling. The personnel must meticulously watch every drop. They constantly monitor pressure, flow, and tank levels to prevent overflow. In submarines, diesel fumes can become trapped in cramped, unventilated compartments. Therefore, the air is constantly checked for explosive vapors. Safety staff with powerful fire suppression systems monitor the deck and enforce no-spark zones. Every electrical device near the fueling station must be explosion-proof, and cell phones and open flames are banned. Interestingly, diesel fuel does not always turn the propeller. Diesel engines power massive battery banks in most modern designs. When submerged and hunting, the sub runs silently on pure electric power, making diesel tank refueling its stealth mechanism. Using buoyancy, submarine refueling is a high-stakes physics experiment. Adding thousands of liters of fuel weighs the ship down. Weight and balance are crucial in submarining. The crew calls this trim. The submarine bow will sink if the forward fuel tanks are filled too quickly. When aft tanks fill too fast, the stern drops. Fuel is stored in various internal tanks, designed to distribute weight equally across the hull to prevent the submarine from tilting or becoming unstable at the pier. The crew must constantly adjust internal ballast and compensating mechanisms as fuel enters. Many diesel-electric designs replace fuel with seawater during long missions in a compensated fuel system. To prevent the submarine from becoming too buoyant and surfacing during a mission, this maintains its weight. Ship stability calculations must account for every gallon of fuel added. A constant mathematical balance game. However, refueling nuclear submarine propulsion systems requires industrial surgery far more difficult than balancing a diesel boat. The sea's greatest predators are nuclear submarines due to their endurance. The vessel's tiny nuclear reactor creates immense heat. This heat generates high-pressure steam that powers ship and crew life support turbines. Nearly incomprehensible energy density of nuclear fuel. Golf ball-sized uranium generates more energy than millions of gallons of diesel. Modern nuclear submarines can stay submerged for decades if the crew has enough food. The reactor doesn't need gas, yet the submarine needs supplies and upkeep. Virginia-class submarines' new reactors last 33 years. Older or midlife refitted classes run out of gasoline. That day's engineering is unique. To open a hatch and remove fuel requires a multi-year industrial marathon. A nuclear submarine refueled at a dry dock-equipped Navy shipyard with nuclear certification. Start with cool down. The reactor is shut down, and the decaying isotope's heat must be managed for a considerable time before work begins. Radiation protection staff maintain the vessel in a controlled environment. They prevent radioactive leakage with huge lead shielding and advanced monitoring and containment systems. The reactor is deep in the submarine's most insulated part. Therefore, ordinary doors are too small. Workers may have to dismantle massive equipment, pipe, and wiring to reach the reactor compartment. For a hull cut, engineers use torches or saws to cut through the pressure hull's thick, high-strength steel. Similar to serious surgery, not ship maintenance. A billion-dollar submarine with a massive spine hole illustrates this operation's scale. Once the reactor is open, used nuclear fuel is removed. Extreme caution and remote handling technology define this process. Dedicated equipment is lowered into the reactor compartment to remove spent fuel assemblies. These components are radioactive and generate decay heat, hence humans never handle them. Instead, insulated transfer lines or underwater canals transport them to lead-lined containers. Dozens of sensors and nuclear engineers record every move. Used fuel is transported safely in transport casks to an approved storage or processing facility, where it will be managed for decades. The submarine's area is one of the most monitored on Earth during this phase due to strict safety protocols. After the fuel is removed, the reactor vessel remains dangerous, requiring regular ventilation and shielding to safeguard the workers who will install the ship's new heart. The process pivots on installing the new nuclear core. This new fuel is handled with the same care as the old fuel, but it is less radioactive before a fission reaction. The hardest portion of rebuilding starts when the new core is installed and the reactor is rebuilt. Engineers must rebuild the submarine, account for every severed pipe, disconnected cable, and lead shielding. Pressure hull restoration is extremely important. The cut-open submarine section must be welded back together perfectly to withstand deep ocean pressures. Welds are X-rayed and ultrasonic tested to ensure no microscopic flaws. Refueling is often paired with major modernization. The Navy will install new sonar, electronics, modern weapon systems, and hull repairs while the ship is open. This explains why a nuclear refueling, or RCOH, can keep a submarine out of the fleet for 2 to 3 years. A number of rigorous tests must be passed before the submarine may return to the silent depths. The reactor reaches criticality for the first time in years during dockside system inspections. Engineers meticulously monitor heat and pressure. After propulsion system testing, the ship undergoes harbor and sea trials. sea experiments stretch the submarine to its limits. It does high-speed runs and crashbacks, where the engines reverse at full force. The submarine's dive trials, where it slowly drops to its maximum working depth, are unnerving. Engineers listen for structural complaints and assess the entire hull for leaks. They must verify the vessel's nuclear power plant and pressure-resistant underwater craft safety. Every sensor must be faultless before the submarine may return to the fleet. A diesel-electric submarine is refueled like a complex ship to summarize our incredible contrast. Hoses, conventional fuels, and weight control keep it balanced and discreet. Any well-equipped naval base does it regularly and quickly. Refueling a nuclear submarine is like rebuilding a power station in a steel enclosure. The ship must be dismantled and reassembled, a tremendous engineering task that occurs just once or twice in its lifetime. One relies on fuel supply lines, while the other uses a single, massive energy investment to dominate the oceans for decades. The engineering behind these vessels is astounding. A diesel boat's meticulous balance or a carrier killer's nuclear surgery, refueling is naval power's silent heartbeat. Next, should we explain how submarines make oxygen from seawater, how they survive abyssal pressure, or the horrifying methods operators employ to escape a disabled submarine? Share in the comments. Enjoy this deep dive into naval engineering? Check out our other movies on the world's most sophisticated machines. Thanks for watching. See you next time.